Have you ever experienced this? You open a program and suddenly your computer freezes for a moment. The fan starts spinning like crazy. A few seconds later, everything returns to normal. So what just happened? What's going on behind the scenes? The answer lies in the layered architecture of the modern operating system quietly doing its job. From the moment you click that icon, your OS goes through a tightly controlled sequence, transitioning from user space into the kernel via a system call, then using drivers to interact with the hardware. Today, let's break it all down with a single diagram to understand the full picture of how a modern operating system works. Why do operating systems use a layered design? Think of going to a high-end restaurant. You sit at your table, order food, and wait for it to be served. You don't go into the kitchen or touch the stove. Operating systems work in much the same way. They separate application logic from low-level system resources and provide abstracted interfaces so apps can run safely and efficiently. This separation forms the foundation of the user space and kernel space model. No matter if you're using Windows, macOS, or Linux, they all follow a similar layered architecture. Each function of the OS is structured in tiers based on dependency from the hardware abstraction layer at the bottom, through the kernel handling memory, file systems, etc., up to the system calls that connect to the user space. Each layer only interacts with its adjacent ones. The lower layers provide services to the higher ones, and the upper layers call functions from below. This keeps things clean, modular, and maintainable. Lower layers closer to the hardware run in kernel mode, while higher ones, like user applications, typically run in user mode. What's in user mode and kernel mode? User space includes apps, libraries, and user-level threads. These components can't directly access hardware. Instead, they communicate with the kernel through system calls, kind of like how restaurant customers place orders without stepping into the kitchen. Kernel space is the core of the operating system. It has full access to system hardware and handles critical operations like process scheduling, deciding which program runs next, memory management, allocating and freeing memory, file systems, managing file read, write, and disk access, networking, sending, receiving data via protocols like TCP/IP, interrupt handling, responding to hardware signals, device drivers, managing interactions with physical hardware. Even when you're downloading files, gaming, and streaming music all at once, the kernel ensures everything runs smoothly. System calls are the gateway for user applications to safely interact with the kernel. Here's what happens under the hood. A user app requests an action, like writing to a file, through a library function. For example, print in C, which internally calls write. This triggers a system call instruction, such as syscall on x86 or svc on ARM. The CPU switches to kernel mode, saves the current user context, and loads the kernel stack. It looks up the system call number in a system call table, verifies parameters for safety, and executes the corresponding kernel function, for example, writing to disk. The result is saved, the CPU restores user context, and control returns to the application. This entire process allows apps to request privileged operations while keeping the system secure and stable. Why layering matters? A layered OS design brings several advantages. Security, user space crashes don't affect the kernel. Isolation, programs can't access memory outside their own space. Maintainability, each layer has a clear responsibility and interface. Modularity, developers can update or replace components independently. Modern operating systems rely on this structure to ensure your system runs reliably, no matter how many apps or devices are involved. Although Windows, Linux, and macOS all follow a layered model, their internal architectures differ based on history, goals, and use cases. Windows, for example, Windows 10/11. Windows uses a hybrid microkernel architecture, specifically the NT kernel, designed for broad compatibility and enterprise reliability. Key components include NT kernel manages core tasks like scheduling, memory, interrupts, and IPC. Executive provides higher-level kernel services like file systems, memory management, security, ACL-based, and I/O coordination. Hardware abstraction layer, HAL, isolates hardware differences so the OS can run on diverse systems. Driver stack, most drivers run in kernel mode. Some run in user mode for safety. User space services include GUI components, PowerShell, system services, and compatibility layers like WSL2, which runs a Linux kernel using virtualization. While performance is important, Windows puts a strong emphasis on compatibility with legacy hardware and software. Linux is based on a monolithic kernel with support for dynamically loadable modules. It's designed for flexibility, customization, and performance across everything from embedded systems to supercomputers. Core features include kernel, runs everything from process and memory management to device drivers and the networking stack. Kernel modules, let you add features like drivers without recompiling the kernel. System calls, provide a standardized interface between apps and the kernel. User space tools, shells, for example, Bash, ZSH, systemed for service management, glibsh, and desktop environments like GNOME or KDE. Linux emphasizes performance and freedom. It's open source, highly configurable, POSIX compliant, and supports the Unix ecosystem. macOS uses a hybrid architecture combining a Mach microkernel with a BSD subsystem, offering Unix compatibility and seamless integration with Apple hardware. Core components include Darwin kernel, the foundation of macOS. Mach microkernel handles low-level tasks like scheduling, memory, and IPC. BSD subsystem manages file systems, networking, and security using Unix standards. IOKit, an object-oriented framework for device drivers, supports hot swapping and power management. User space includes Aqua GUI, Quartz, Rendering, Metal, API, Cocoa, Swift UI frameworks, and compatibility tools like Rosetta 2 to run x86 apps on ARM chips. macOS balances stability, performance, and tight integration with Apple's hardware, especially M-series chips. It combines open source components like Darwin with proprietary ones like the UI. Why these differences matter? Windows originated for personal PCs and prioritizes wide hardware-software compatibility. Linux grew out of the open source community to replace Unix, focusing on flexibility and control. macOS evolved from Next Step and merges Unix reliability with elegant user experience and deep hardware-software integration. Understanding these architectural choices helps you choose the best development platform and write faster, safer, and more reliable software. We started today by looking at how modern operating systems are layered. We explored the roles of kernel and user space and compared Windows, Linux, and macOS in depth. Behind every click, scroll, and program you launch lies an intricate system of logic, hidden order you interact with every day. Want to dive deeper into system call mechanics, paging, driver development, or kernel scheduling algorithms? Let me know what you're most curious about. Don't forget to like, subscribe, and turn on notifications. See you in the next video.